Hi, my name's David, and I'm making this video to show how the compression gradient tool that I made works. It's made in Python in the Google Colab environment, and it's publicly available. Links in the description if you want to use it. It creates images like these. You can see the original images on the left and these modified images on the right. And so the whole purpose of this script is that it takes an image and basically it compresses it in different ways, and then it combines those different compressed forms to attempt to create a kind of gradient of compression. So you can see that especially on this image of Usain Bolt, where the compression is actually more prominent the further away from him you get. So that's the kind of purpose of this tool. So again, you can use it if you like in the Google Colab, but this video I'm just going to be talking about how the code works. So with respect to Python, I'm going to try and walk through and demonstrate the problem-solving strategies. And in addition, basically what this will provide is good practice in using lists, including nested lists and a variety of indexing strategies for data sets. Also, this project introduced me to matrices with Python, and at a surface level, how to work with images represented as matrices. Okay, so to get into it, it's tough to explain how code works because it's difficult to nail the right level of resolution at which to work, at which to operate. So I'm going to start off showing how it works at a somewhat high level, and then we can work our way down and get a better sense for how the guts of the code work at a lower level. So before I'll do anything else, I'll just make a cursory introduction of the singular value decomposition method, which is the method used to compress the image. So the singular value decomposition method allows you, it's a means by which you can have some sort of data matrix. So let's say data matrix D, and that is a matrix. It has all these elements, etc. And by the following method, the singular value decomposition method, you can decompose that into three matrices. So these might be called U, S, and let's just call it V. And V is the transpose is taken of that matrix. So I won't go into the math very deep. Basically, the idea is simply that you have some very large data matrix, and by taking the eigenvectors of the correlation matrices of this original data matrix, those eigenvectors provide you with a basis to construct this one. So the idea is, instead of having however many data points, let's say 1,000,000 in our original matrix, if it's a large image, and you consider one pixel as one element, so you have so many rows of pixels, right, in an image. The idea is that instead of having basically one data point for every pixel, the idea is that we can have some sort of, we can identify a pattern in each column of our data matrix. We could say each column follows some sort of pattern, and that pattern might be described by many building block columns. You might have one column where this is a dark pixel, this is dark, this one's dark. So you have a pattern, you have many different columns. And the idea is that by putting them together, you can reconstruct your original image. So again, I don't want to go into too much of the details about the singular value decomposition method, but it allows you to compress your data by basically being able to represent a given matrix or image or whatever that matrix may contain using less data, by being able to describe it as a sum of smaller parts of building blocks. Okay, so I want to leave that there, and then we'll move on to how the code works with that in mind. So basically, for the purposes of the code, all we need to know is that we have a function. So it's a black box. It takes in a data matrix, and it spits out a compressed matrix. So we might call that D hat. And that compressed matrix is the same size as our original. It's the same size, n by m, whatever the case may be. But the data itself is less distinct. It's not 100%, it doesn't have 100% fidelity. Okay, so I'll leave that there, and now we can talk about the code. So at the highest level, what the script does is it takes multiple images, each one at a different level of compression. So let's say we have red is very highly compressed, so it's low fidelity. And then let's just say that we go blue is very compressed, but not as much as red. And then green is just a little bit compressed. And then actually, instead of saying green, I'll just say purple. Then we can say purple is just a little bit compressed. So, and then green we'll say is our original image. So this is a data matrix. You'd think there's one element for every pixel in your original image, so it's a big array. So this is an image, right? And these are sequentially more compressed. So this one, it looks a little fuzzier. And then this one looks more fuzzy, and it just keeps getting fuzzier and fuzzier, right? Because it's more compressed. So that's something about the idea. So how this code works is that it simply you start off with your original image, right? And that's, let's say, this big. And what happens is it overwrites it with the most fuzzy one, and then it overwrites that, but a smaller subsection of it with the less fuzzy one. And then once again, it overwrites that, but a smaller section again with the one that's even less fuzzy than that. And then lastly, it does one more overwrite where it overwrites a smaller section, which is actually defined by the user, with the original image. So what you end up with is a central area, or whatever area that you define, which is high fidelity. So we'll say it looks like there's your smiley face, and then you have so that's the whole point, is to make a kind of gradient of a trend which goes to lower fidelity. So then this one is fuzzier, right? And you get the idea, hopefully, where simply by overwriting these different areas of these matrices, you end up with what looks like a gradient of compression, but really it's just multiple differently compressed images being copied and pasted and layered over one another. Okay, so that's how this works at a very high level, no code involved. So now trying to get at a lower level, this description that we have here reveals basically the sub-problems that we need to solve. So to get this done, we need to question how many images to include. So in this example, we had 4, but why 4? Like, how many should we have, right? That's a question. And another one is, how should we go about to creating these and storing them? So when we have work in progress, how do we create it and store it? And another thing is, what shape should the overlap be? So in this example, I've shown it as columns, but like, could it be a row? Could it be a square? Like, what shape could it be? That's another problem that's just up in the air at this point, so we'll talk about it. And lastly, how can the overlap be implemented? In terms of actual code. And not only that, but what are the parameters? What is the width of each band? The height of each band? Like, how do we know that we're going to assign that much and that much? You know, we need to tell the computer all these things. So having those problems, we'll pretty much get into that and talk about essentially breaking down how I went about answering each of those questions programmatically. I'm going to try and focus more on the abstract ideas rather than trying to do a line-by-line breakdown of the code, although I might refer to it at some point. So for the first question, how many images? That can be answered straightforwardly with respect to the singular value decomposition method. So like I mentioned, the idea with this is that instead of having a million data points or whatever, this method allows us to consider this as in a collection of data that's built out of a limited number of data blocks. So as here, we could think about this as 1 million different unique data blocks. And instead, what we end up with is the idea that, let's say we have 20 building blocks, and then each element of this array is some unique combination of those blocks. So what gets stored is only how to combine them. That's the idea of the singular value decomposition. So essentially, when we ask, okay, how many images are we going to create? Well, we can determine that based on this number. The higher this number, the more fidelity our compressed image will have. The lower this number, the lower fidelity our image will have. So by asking the user, and you can go and use this code on Google Colab, by asking the user what, this is called the rank, what rank we want the image to be, giving a range, then we can know that, okay, within that range, 1 to 10, whatever the case is, that we're going to have 10 images. So that answers the question of, okay, how are we going to construct this gradient with respect to how many images do we have? Secondly, how do we create them and store them in work in progress? That's pretty straightforward as well. The solution I had here is basically to create a list to contain those variables. So again, in Python we have a list data type where it can store multiple entities, and it can be added to at any time, or you can take things out at any time, and the list will shrink. So the list is the ideal storage unit for this. And so pretty much we just have a loop where within our loop we iterate through this however many times until we're done going through all the ranks. And basically every iteration we just add a matrix to our list. So in this case, each one of these will be an image. Image 1, image 2, and so that the image is actually a huge matrix of data points, each one representing a pixel in the original image. So we have a list of matrices. So what that looks like over here, is right over here, we have 4i in ranks. So we're iterating on I through ranks, and ranks is a matrix containing the ranks, the integers that we're going to use, and then we just compute our x SVD, which is our data matrix X using the SVD method, and then we append that to our collection. So the append is just the method applied to the list. So that's what that code looks like right here. So that's how we can create and store these different matrices. And at this point, I'm going to point out something that I neglected to mention earlier when it comes to rank. Okay, there's this phenomena with the singular value decomposition method where you have, let's say this is your fidelity of your compressed image. So the higher the fidelity, the more accurate to the original. And then this is your rank. So this is the number of building blocks that you have that you create so as to create that original image. The idea is that if you only have the first few building blocks contribute disproportionately to the fidelity of your recreation of the image. So the graph looks something like this. So what we see is that rank 1, 2, 3. Well, actually, I'll actually make those even tighter. We have rank 1 over here, rank 2, rank 3, rank 4, etc. You see that by, if this is, let's say, 50%, and this is 100, the idea is that by rank 4 or something like that, we're already at 50% fidelity. And then to get to 100, it might be something like 600 or something large. So basically, we have exponential drop-off of the contribution that each rank makes. So if you make a graph that says, let's try and make that a little smoother. If we have a graph that says fidelity contributed and for each rank, well, the first rank is going to contribute a lot of fidelity, and then the second one is going to contribute much less, and then the third one less than that, etc. So we have this kind of situation. So here's the problem. If we want our gradient to appear linear, if this is a strip from our image, and we want it to be crystal clear over here, and then over here we want a little bit of compression, and then in the next part we want more, just a little bit more, but not so much more that it looks jagged, it looks rough. And then here we want a more significant amount so it looks more compressed, and etc. You get the point. If we want our compression itself to look linear, then we want some sort of collection of images, so our constituent images. Earlier I had used red, blue, green. So if we want this to look linear, we want our fidelity, let's say fidelity over here is something, so we have our good image beside this one. Let's say our fidelity is, our good image is green, so this is 100% fidelity. And then our blue image, let's say we want it to have 80% fidelity. And then our red image wanted to have 60%. So we can see that the delta here is minus 20%. And the delta here is minus 20%. So this is what we want. We want a linear decrease in fidelity. But if we just said, okay, this one is going to be rank is equal to 1, the original image, the green image, 100% fidelity is not compressed. So if we said, okay, this one is going to be rank equals, let's say, so 80%, so it might be 100, rank equals 100, and then this one, rank equals 99, that's not going to work. And if we tried this backwards and said, okay, let's start at the worst possible, the most compressed possible image, let's say rank equals 1, then if we go up to the next one, rank equals 2, this isn't going to work to give us a linear output because of this line right here. What we're trying to create is we want to achieve something where we pick certain ranks so that the line they create appears almost linear. We want a straight line, right? So that's the problem with, that's the reason we can't just go through every rank, is because our gradient would not appear linear. Okay, so having explained all that, what I used to solve this was the following method. We can see it over here in the code. So I said, I let the user define the rank step. So like I said, going one by one is not going to look smooth, but I allowed for the user to define their own rank step. But if you define rank step as -1, then I have this default method that takes over control. And this is what happens here. It essentially takes in the minimum value you provided. So let's say we had min rank and max rank, which were provided by the user. So let's say this was entered as 1 and this was entered as 10. And what happens here is that we see it creates a new list with each of these entries squared. So we would have a list now for our ranks, and it'd be 1, 4, 9, 16, 25, etc. squared, every value squared until 100, right? And then the idea is that if we take each one of these ranks, now we're not stepping up by 1 at a time. Now we're stepping up by bigger steps every time. So we're starting here, we step 1, and then we step 3, and then we step 5, and then 7. You see that as you follow x squared, you're taking larger and larger steps until you reach 100, whatever the case may be. So then the idea is that by having those steps that are more and more disconnected, we can have a better approximation of a linear gradient. Let me just make this one thicker. Let me draw a new line. If it's not so steep, this yellow line was an exaggeration of the steepness. It might look something like this. So now if we are looking at these points we've defined, let's say these, now the hope is that by connecting these lines, which have by following this path, which has larger steps, the hope is that our outcome might be more linear than if we had just gone through every single one of those ranks and created a compressed image for each one. Okay, so after having this list, I also felt, after doing some test runs with it, I just felt like there wasn't enough data being made, so it did not look very smooth. So then I added this other line of code over here, which basically inserts, it's just this few statements over here, basically just linearly interpolates. It says, takes the average of these, so add them and then divide by 2, and you have to round down. You need the ranks to be integers only. So this basically inserts numbers in the middle. So this whole list becomes 1, 2, 4, 6, 9. You see the pattern. It's just adding the numbers in the middle of these ones that we had interpolated before, 25. So then this goes all the way, etc., 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 until it reaches, until we end up adding, we have 81 for 9 squared, and then something like 90. So just by adding more data points, it becomes smoother. Okay, so far we've offered solutions for basically how to answer these sub-problems, wanting to create this compressed image. We've seen how we can create and store a work in progress, and we've seen how we can compute how many we want to make. Okay, when it comes to what shape should our overlap be, basically I allowed the user, and again, you can try this yourself in the Google Colab, link in the description, but basically we allow the user to create to just decide whether they want horizontal bands, vertical bands, and so we have examples of these at the bottom over here. So here we can see Usain Bolt. This example is a vertical band, I believe, where it's 100% fidelity in this vertical strip around his body, and then it's losing fidelity as it moves away. And then we have horizontal. This is a square, so here it's losing fidelity in every direction, moving away from the crocodile's eye. A little harder to tell in the water here because it was already kind of blurry, but you can see on his nose and above his head and below his head, it's losing fidelity every direction. And then there's the horizontal strip where fidelity is maintained horizontally. And then there's the cross, so this just combines the two, where this image has 100% fidelity around his face, both directly above and below, and in the same row, side to side. And then lastly, there's the multi-focus area blend. So we'll get to that in a bit. So the next question was how do we decide how to overlap these? What are the parameters for the width? So this is kind of important because the hope with this little tool is just a little something fun to be creative and to modify images. So it's best to give the user as much creative control as possible. And so I really did want to be able to allow the user to determine whether they wanted that compression to be slight and travel slowly per se, or have it be very heavy and be implemented over a short space. So that's the idea of the gradient parameter. That's the idea of how wide are these bands. Are we providing more weight to the higher resolution bands, more weight to these two and then less weight to this one, or the opposite? So that's the kind of creative control I wanted to provide. So then here's how I did that. Basically, what it comes down to is that we have these bands of the gradient, right? Like I mentioned in that description above, where our final output is just being created by overlaying. Whoa, didn't mean to do that. Our final output is created by just overlaying these different smaller sections of the images. So each image has a corresponding number, which is its rank. So then the idea was we can create some sort of function where it computes for us a width based on its rank. So we will have some rank over here, and then width of that band, right, of the gradient. And so then we can determine if we want it to look something like this, or if we want it to look something like this, or maybe we want something like this, or something like this. So that's the kind of solution I was able to make, and so here's how it works. I'll just find it in the code and we can take a look at it real quick. So the idea is that each rank is given a weight, and the weights help to determine how much of the space that a given rank gets. So let's say we have our image here. Instead of drawing it, I just remembered I can actually copy and paste something. So let me just pull one up and paste it in. Right. Okay, so here's the idea. We have an image, and we want to define the area that we want to stay high fidelity. So I'll just say that's the vertical strip over here. We want this area to be high fidelity. So then the idea is, okay, we have a certain amount of space, and this is quantified. This is a known number of pixels. So this is n, let's just say it's n number of pixels. The idea is for each rank, we can compute a function. So we can say that we have a function for our rank which gives us a weight value. And then we can say that each rank, each image corresponding to a given rank gets a certain percentage of this space, so a percent of n. And that percentage of n that it gets, the real estate it gets, corresponds to how much weight it has out of the total. So here's what that looks like in practice. I decided to go with the power function. So we have the rank gets evaluated by using exponent. So basically, our function of a rank is equal to our rank to the power of some number, and that's equal to our weight. So we could do that in practice. So let's say rank, let me just make that thinner there. We can say rank is equal to 1, 2, 4, just for the sake of the example. And so having that, we could say that n, for the sake of our example, n is equal to 1. So what does this mean? This means that our ranks 1, 2, and 4 will have weights of each one to the power of 1 is just itself. So if they have weights of themselves, then as I mentioned earlier, the percentage of n, let me just make that in there, the percent of n that each one of these gets is equal to the w over the sum of all the w's. So in this case, what that looks like, so this is w over sum of all the w's, weights. So what that looks like is that we have 1 over, 6. 1 plus 2 plus 4 is 6. We have 1 over 6, 2 over 6, and 4 over 6. Sorry, I'm just quiet for a second because I'm surprised that this isn't, I don't think it's showing what I want it to. This might be an error in the logic, but we'll see. So the idea is that, oh my gosh, it's 7. That's why I was getting so spooky for a minute there. All right, quick correction. 1 plus 2 plus 4 is 7. So we have a percent of n. So this is going to be 1 over 7. One's going to be 2 over 7, and then this is going to be 4 over 7. So that's important because this adds up. The sum of that is equal to 7 over 7 is equal to 1. So the idea is 1 over 7 in percentage. Let's just say we split this into 7 parts. 1, 2, 3, 4, 5, 6, 7. Okay, got a little bit smaller at the end. No big deal. The idea is going to be that this one part is going to be rank 1, the image that was according to rank 1. And then this part over here is, so now we're going to count out 2 of these portions, and 2 of these portions is going to go to the image that corresponded to rank 2. And now we'll count out 4 of these portions, and 4 of these portions goes to the image of rank 4. So if we break it down this way, we see that what we end up with is a gradient something like this, where we have a portion over here, which is fairly sized, which is a fairly good approximation. So rank 4 is going to be a much better approximation than these two. And then we have this band. We have this band of this image vertically over here, which is worse than that, but it's not the worst there is. And it's still somewhat wide. We can say this region is somewhat of the same compression. So it's like this. We have half that size region as before, worse off. And then lastly, we have a thinner region at the tail end here, which is really compressed, highly compressed. And so then that's the idea here. So we have highly compressed region, and then we have kind of a middle compressed region, and then we have a region that's more lightly compressed. So you get the idea of how you can distribute your different images that have different levels of compression across the space. And likewise, the same thing would occur here for the other side. So the other side of this gradient would be split into 7. 1, 2, 3, 4, 5, 6, 7. And then one of these would go to R1, and then 2 would go to R2, R equals 2, R equals 1, and then lastly 4 of them would go to R equals 4. So we get the same kind of gradient in the other direction. Okay, now what's cool to see is that this method offers a lot of flexibility because it's a function of n. So this is actually not just a function of r, it's actually a function of r and n. So the user gets to define both of those. And we can just take a look and see what happens, what's the relationship to n. So I'm pretty sure it's going to correspond to these ones. So if we have n is greater than 1, let's say it's 10. If we have n is equal to 10, then let's just say I'm going to show the weights over here and the rank over here. So the idea is that for n equals 10, the weights over here will be, well, 1 to the power of 10 is 1. 2 to the power of 10 is, well, it's something really big. Let's just say 10,000, even though it's much bigger than that. And then lastly, 4 to the power of 10 is something even larger. It has a relationship because 4 is 2 to the power of 2. So we might say that's a million, just for the sake of quickly evaluating this. So we can see how then, given the weights are 1, 10, and a million, the percentage of n over here the percentage of n is going to be something outrageous, where this is going to be ludicrously small, and this one is going to be smaller than that, but still very small, and this one is going to be an enormous proportion of n. So what we see here is that an n of a positive number corresponds to this green line, which is exponential. So n is some large positive number. We end up with exponentially greater weight being given to the higher fidelity areas of the image. Then, if we just analyze something else, so if we say what happens when n equals 0, when n equals 0, the weights are equal to r to the power of 0. So any number to the power of 0 is 1. So all of these weights would be 1. And then this is interesting because actually what results is that you have equal proportion of n for every rank item. So I actually neglected to draw that on the original one, but we have this scenario. So when n equals 0, every different image that we have, all the collection of images that are compressed to different degrees will get the same real estate on our image over here. And then let's say if n is negative, and it's a very high number, we're going to have the same thing we saw except in reverse. So let's just look at that. So 1 to the power of negative 10 is 1. 2 to the power of negative 10 is some really large negative number. So negative power is going to go 1 over 2 to the power of 10. And so it's going to be a really tiny number. So it's going to be really, really, really tiny. And then 4 to the power of negative 10 is going to be So 4 to the power of negative 10 is going to be some sort of just ridiculously small number. So then what you end up with is these weights being the opposite proportion as to what we saw before, because 1 out of 1.00000000 is nearly 100%. So we end up with that kind of scenario. So that's why if we have a very negative number, then we end up with the opposite exponential. Here, n is a negative, very negative value. And then if we just do another example, so I'll just continue that off to the right. The last example I'll show is where n is a small value, less than 1. So if n is less than 1 and greater than 0, then what we have is it's performing kind of a square root. So let's say it's 0.5, 0.5. So that's the square root of r. So the square root of 1 is 1. And the square root of 2, root 2 is like 1.4 or something. And then the square root of 4 is 2. So the weights then become, so this can be 2.4 plus 2 makes 4.4 total. So 1 over 4.4 is going to be something like 22% or something like that. And then 1.4 over 4.4 is going to be something like 30%. So for the sake of this example, we could go at 28%. And then lastly, 2 over 4.4 is going to be a little less than half, but we'll just say it's 50% for the sake of the example. So these should add up to 100%, right? And so you see how this is providing a less extreme gradient than these exponential gradients looked. And so and the value is increasing towards the higher fidelity. So we could say that this blue line over here is n is less than 1 and greater than 0. And then lastly, I won't go into the details, but the numbers just kind of reverse if you have a negative exponent. So over here, if we have -1 and n is greater than -1 and it's less than 0, then we have a negative square root. So we're taking the weight is going to be 1 over root r, or the nth root of r. So that trend will be kind of negative linear. So this is how I went about computing the weights, the width of each band in the image. Really great property of this kind of power function, which allows all these different modalities. So that looks like this in the code. We basically have our evaluation function here, rank number to the power of bandwidth, and then what we do is we create a list, which is eval, so the values resulting from evaluating the power function. So eval is equals evaluate function with argument I for each argument in ranks. So this will create a list with all the weights, and then weights is a list where we take each evaluation outcome and divide it by the sum of the other weights evaluation outcomes, and that will give us our weight as a percentage. So then we have our weights, and from there it's pretty straightforward matrix operations, essentially to take our different matrices which contain our compressed images. So we can look at this example here. Basically what we're doing is we're saying that our data about where the bound is for a given image. So let's say that we knew we had a bound right here and right here for our different forms of compression. Then we iterate through those bounds. Okay, so let's look at this one first, and then let's look at this one second. And for each one of those bounds, we just look at each image that we compressed, and each image has its own unique bound. And basically, so for that bound, we just use this slicing method, and basically we're picking out, we're using the number which gives us the pixel coordinate where the bound is, to pick out a subset of pixels and paste them on. So it's like I showed at the top here. We have our basis, which is going to be our most compressed one. And then so this is a data matrix. This is D. This is actually represented by a data matrix with all these pixels. And then we simply have an analogous data matrix, which is less compressed. And all that we do is just use these slicing method in Python to just select a chunk of this and plop it right into that data matrix. So by using slicing both in the left side and right side of the equation, we can select entire chunks like this and drop them in and overwrite previous stored data. So I'll leave this video there. Basically, that's how I went about creating this program. So there's a great practice with indexing. You can see there's lots of nested lists going on. I have triple nested lists over here. Great practice with indexing, and so anybody can feel free to look through this code, links in the description, and use it for fun, and try and even follow through and see what it's doing. And feel free to support me on Patreon, and then you can get this code with comments. There's plenty of comments throughout saying what every single line is doing. So I hope this might be interesting and helpful. So thanks for watching. Take care.